Yeah, okay, I'll
So
try to
please.
do that in 30 minutes.
Sure.
Okay, so this is a high-speed talk. These are the things that I'm going to try to talk about. There's 4 themes. It's a mixture of kind of a status check. Satoshi, I'm not talking about Aurora, so I mean we can talk about Aurora over Saki, but what this talk is about 4 things. In exascale, what might we do together to keep momentum, and also to figure out how to teach the next generation how to work together, because everybody in here is, not everybody in here is old, but a lot of us are old. So we've got to figure out how to fix that. Second part is about AI, and it's changing everything, and it's going to impact us. I was really surprised at both the talk from Satoshi and actually Sai's talk also about imagining AI is just going to be a small fraction of the workload. So I will maybe challenge that a bit. But we need to own the AI and science coupling, not have the tech companies own that. As much as they do good work, I think the science community needs to own that. I'll talk about quantum. We're starting to see cracks appearing in their plan. But what actually should we be doing such that 100 years from now, when history renders judgment on us that we did the right thing in quantum? Not clear. And then I'll talk about Zeta and why we actually need to work on Zeta in spite of all the other things that are going on. So this is kind of high speed here. So we're entering the kind of post-exascale regime, right, after having achieved it. And the real question that we should ask ourselves is, what should we be doing next, right? And in this context, what should we be doing together, right? And I think there's a number of things that we can do that kind of make sense. So one is, standing up these big exascale machines is hard work, and yet we haven't really captured the process of doing that as a science of large-scale systems. I think we need to do that. It's something that we need to encode so that we get better at doing that. And we need to figure out what expertise do we need in the science community for standing up big machines that's different from what the hyperscalers are doing. If there is no difference, ultimately it'll be harder and harder to maintain separate computing infrastructures. We've got to fulfill the promises that we made to the community and to the governments on the impact of exascale applications. So how do we get more adoption? In the US, the ECP strategy is kind of weird because just as we stand the machines up, right, we're stepping down the ECP, and there's hundreds of apps that still have to be ported on the machines. Maybe we can figure out better ways of sharing codes and workflows. Maybe that's something we can do together. And then protect the investments that we've already made. I think there's many of the investments in the software stack probably will bear fruit for a decade if we can figure out how to do that. So what should we do together? These are some of the questions. Now, there's a handful of things that I think now become possible that, or a way of thinking about things that was not really clear 10 years ago when we started doing this. And I'm not going to read this slide, but I'm just saying that many technical problems can be framed as high throughput workflows with a bottleneck. And the exascale is the piece that's solving that bottleneck right now. But in the future, that bottleneck may be solved by an AI surrogate, or it may be solved by a quantum accelerator or something. And Satoshi kind of mentioned this in his talk. So that's something to think about, how we reframe our problems. Another one is AI managing simulations. And I'll show you an example that we're working on, but there's lots of ways to do this. And the third one is AI surrogates, where we're accelerating. And Satoshi also talked about that. We've had a lot of people using the term digital twin, and I think to me what that means is, rather than modeling a generic instance of something, we model the actual instances, the many actual instances with actual life histories gathered through, say, edge computing and sensors. This is how I think the notion was actually invented, and it applies to all kinds of things: jet engines, humans, power generators, buildings, spacecraft, whatever, right? And if you do this right, it's going to dramatically increase the amount of computing we need. Orders of magnitude more, because instead of modeling a generic instance, you're modeling the thousands of actual instances of something, right? That's got to be computed somewhere, right? So this is going to drive this whole notion of data-driven simulations. I think we're underappreciating the transform aspect of that. Okay, AI managed simulations. This is something that we're prototyping in the context of radiation biology. This is a interesting exercise that actually at DOE is being funded by BER, not by Oscar. It's a amazing concept. So we have this simulation in the gray box here. That's a mechanistic model of, say, how radiation interacts with human tissue. And we're wrapping it with a foundation model that knows how to actually extract concepts out of the literature, adjust the physical constraints or the structural constraints on the model, regenerate a model fit against real data, and then we use the AI to actually read back on the simulation and adjust this. This is kind of like a self-driving simulation concepts. And it's very interesting. This is something we could obviously collaborate on in general. Another topic that is come up in the current multi-lab exercise in the US about interacting with vendors about where we want to go in the next 5 to 10 years. And there's this concept that we need a better name for it, but this notion of, can we build a base infrastructure, racks, cooling, power infrastructure, say passive optics, and then define strong module interfaces such that we can work with the technology developers around modules that interface these strong standards that will allow us to replace modules on a fast time scale, but not replace the base infrastructure to do that. And of course, there's things like this. The Open Compute Project is trying to do this, but I'm thinking something very specific on the needs of HPC centers. And there's quite a bit of interest in this concept from HPE and Dell and Intel and some of the AI accelerators. So this is something, again, that across the community of HPC centers and developers, if we could work together on defining this and then use it in our procurements, it might actually save us money in the long term. Let me talk a little bit about what happened. This is kind of a funny thing happened on the way to the forum kind of concept here, if you know the story. On the way to AI for Science, right? So in the summer of 19, there was 4 big workshops. 1,300 people in the US participated in these workshops where we laid out research opportunities in AI for science. And it was very focused by the 3 science labs, although all the other labs participated. We produced this report, and then COVID hit. And momentum basically stopped a little bit in terms of the community. But at headquarters, within the DOE programs, there was a lot of momentum that was maintained even through the pandemic, and there were additional reports, some of which had happened before and some of which happened later, that resulted in programmatic money going into this AI and machine learning in the context of science. And this was just a blurb out of the Senate appropriations in 21, where they say not less than $120 million in the Office of Science to be spent on this machine learning across the Office of Science, and even talk about the development of foundational artificial intelligence and machine learning capabilities, et cetera, et cetera. So they kind of got the message, even though a big initiative didn't really roll out of it. There was a lot of small initiatives, and lots of projects got spun up during the pandemic time. And one of the things that we did at Argonne, in conjunction, both at Argonne and in partnership with the other centers in DOE, was set up a AI test bed, hardware test bed. Now it's got 2nd generation gear from Cerebras and Samba Nova, but gear from GraphCore, Urbana, and Grok. And this is open to the community to allow people to experiment with AI accelerators, these novel things that are not integrated at scale yet, as a way of gaining experience to figure out, does it make sense to think about AI accelerators as a fundamental part of future new large-scale large-scale HPC systems. Now, after about a year of a discussion, Doug and I and our colleague Jonathan Carter and our 3 colleagues from the NNSA labs, John Fedema, Rob Neely, Jason Pruitt, and a cast of thousands, organized 3 more giant workshops this past summer. And we embrace our NNSA brethren in this. And so we called these workshops AI for Science, Energy, and Security, and tried to use this to build a community kind of roadmap. This is the report that we're still editing on, but it's going to come out hopefully in the next couple of weeks. It lays out big opportunities. And we framed we're getting kind of smarter as we think about AI. So we framed it along this idea of like, what does leadership in AI look like in the context, in our case, of DOE mission, but in the kind of context of the science community, right? This is AI that leverages big computers, big data infrastructure, large-scale facilities, and our big interdisciplinary teams. And we organized it very differently than other AI workshops that we've seen. We organized it around 6 meta problems. AI for advanced property inference and inverse design, applied to all kinds of systems. AI and robotics for autonomous discovery. AI-based surrogates for HPC, accelerating like effective zeta scale kinds of stuff that Satoshi was talking about. AI for programming and software engineering, getting AI to help us optimize codes, write codes, port codes, debug codes. AI for prediction and control of complex systems like accelerators, buildings, cities, reactors, power grids, right? And foundation models for scientific knowledge. And we've been trying to cross-cut those 6 themes against the broad range of science that's done in the Office of Science and the national security context in NSA, and pull out things like AI grand challenges, those problems where an AI-centric kind of approach can have a breakthrough in some scientific domain. And we heard yesterday a little bit about AlphaFold 2, but using AI, for example, of designing biocatalysts that free us from rare earths for certain kinds of problems we want to do, or designing synthetic genomes, or accelerating key HPC applications, or, for example, optimizing quantum circuits. So there's many technical scientific problems. These are problems that come from, in our DOE context or the scientific community context, around technical or scientific problems. These are not the sweet spots of most of what the AI community is working on. And this is why we need to own these problems. And one of the ways we're thinking about this is this notion of whether foundation models, that is, this idea of moving towards a small number of super powerful models, like ChatGPT-like models, that actually know how to do many subtasks in a problem domain. So we were experimenting with this idea a little bit in the context of COVID. So our group built a series of models for doing surrogate models in doing therapeutics design. And we ended up with this fairly complex workflow that mixes classical simulation and AI equivalence. And we use the classical data to train the AI, and then the AI to accelerate and expand the search, and then drive in a virtuous loop. And there's a bunch of papers on this that we've put out over the last couple of years that I won't go through it, except that in this surrogate context, which is one of the use cases for these foundational models, we were achieving about an 11 million X speed up on the Grok custom hardware for searching for new drug molecules, which if you think about 11 million speed up means that we can search 1 billion molecules in a few minutes, right? Which means you can search trillions of molecules in the course of a week or a month or something, which is unprecedented, right? And we applied this to actual problems in COVID, have a large number of targets. And we've been continuing to push on this idea. Recently, we've achieved over 20 million X speed up on this problem, and it's showing that we can actually do it, and not only focusing on drugs that affect COVID, but drugs that are affecting cancer and antibiotic replacements and so on. But we've been pushing harder on this notion of, can we build a single model that actually knows how to do multiple tasks? So we wanted to be able to predict drug binding, target ligand substrate binding. We wanted to be able to predict the drug response of the organism to that drug. We wanted to be able to classify drug targets and so on. And this is just a plot showing that when we translate all of our surrogate models now into a single transformer framework, we can actually still solve the high performance problems that we built the original system around. So this is kind of amazing that this works, but we pushed it even further. So at this past SC22, the team worked on building a foundation model. It's a large transformer model that we trained on about 200 million protein sequences. And this is a Tisney plot of the embedding that model learned. And then we use that model to generate future protein sequences. For example, we use it to generate future instances of the receptor binding domain in SARS-CoV-2, which is the thing that determines the variant type that everybody talks about and whether or not it increases or decreases the rate of infection. And that that project won the Gordon Bell Special Prize, and here's team members up there. And we collaborated here with NVIDIA and with Cerebras doing these very large transformers. And recently, we've extended this collaboration with Samba Nova, where we have a transformer now where the input window is 32,000 tokens wide, which allows us to not only encode an entire scientific paper as one input instance, but now entire viral genomes as one instance. So we can predict, say, the evolution of a viral genome using this exact same model that's being trained on many bits. Okay, and when you look at this embedding, here's the different cellular functions of the proteins that that this thing was trained on, and you can see how they map against the embedding. And we've used this now to disambiguate genome annotations in a way that's not been done before. That's using the fact that these things have the same function, but they embed to different parts of the space, telling us they have a different evolutionary history. Now, this same idea has been used. This is a group from here in Japan that used the same idea, not the same code or anything, but the same notion in material science, where they built a single model that's able to predict 40 different properties of a molecule or of a substance. So this is showing that there's, I think, a lot of potential for this idea of foundation models, and this is why I think these are going to be much larger fractions of the machine cycles than we or some of the people have been talking about. Now, there's another thing happening in this space that I think is concerning at some level. One is that if you look at the papers coming out of academia, the rate of competitive academic publications in large-scale AI has essentially gone to zero for teams that are headquartered in universities. This resulted in a request a couple of years ago. Again, this started right before the pandemic from the Stanford Center, Human-Centered AI Center, Fei-Fei Li and Etcheman. Sent out letters to presidents of universities saying, this is a crisis. Academic departments are not competitive in AI compared to tech companies. What should we do about it? So they, different agencies convened a study section essentially to look at this concept of a national AI research resource. And they just put out a report. It came out last month. They're asking for $2.6 billion over 6 years. They want to deploy 3 big systems, one every 2 years for $750 million. Right, and then run these things. Of course, the report came out under the signatures of OSTP and Ponch at NSF. And this is what they're asking for in there. They want, this is for the academic community, okay, big machines. They want something like 48 to 60 million quad GPU hours, right? And they talk about how this might be used. 50,000 researchers each get 1,000 hours on the machine to do AI research, or maybe some smaller number of groups, maybe 40 teams could train something like GPT models, et cetera, et cetera. Now, we translated this into how much of Frontier and Aurora are they asking for? Well, they're asking for a pretty huge chunk, right? For the first deployment that they're talking about, it would be something like 60, 70% of Frontier, maybe half of Aurora, because Aurora's got more nodes. But by the second iteration on this, they want to stand up 140 to 180 million hours of quad GPU, which would be both of Doug and our entire systems, right? So this is an interesting thing, right? This is the deficit, in some sense, the academic deficit of state-of-the-art AI capability in the US. And my guess is a similar deficit exists in Japan and in Europe, right? Okay. Now, that's AI. Let me talk about quantum for a little bit. Quantum, I say, can we collaborate in quantum? And the way I think about this, and we have a known quantum denier in the room, which you'll have to guess. Don't raise your hand, Pete. I don't guess who's a quantum denier. But here's the question I'm trying to answer. How to resolve if quantum can contribute meaningfully to solving real problems faster than classical supercomputers? That's the question. I'm not making a good or, I'm not saying it's good or bad or anything like that. I'm not saying whether it's real or fake. I just want to know, is it something we need to worry about or not, right? And so current state, the answer is no, we don't have to worry about it in terms of solving any real problems because these are small machines, they're unreliable. It's this weird circuit model for programming. There's no lack of error correction, lack of good number of killer apps that work on the current hardware, which is 0. A lack of super polynomial speedup candidates that are useful in these small hardware, and lack of have ad hoc integration strategies and so forth. What I'll walk you through in a second is some of the analysis that people have done, and this was hints at this yesterday, right? We need machines with thousands of virtual or reliable qubits, able to run programs, or if you're in quantum head, you think of circuit depth, right? Of something like 10 to the 10th or 10 to the 12 gates, right? So this implies a machine that's at least 1 million qubits, probably maybe bigger than that, and 2 weeks of running if you can get the quantum computer to run at a nanosecond per gate application, which is still not where we are. They're kind of at microsecond levels, right? And we need algorithms that are better than quadratic. So could we actually do this? This is the question I'm asking, right? So, well, how do we get a lot of algorithms? Well, it's people. Maybe AI eventually can work on this, but right now it's people's imagination. So maybe we have to fund 1,000 computer scientists and mathematicians for 10 years to do that, okay? That's maybe doable. We just funded, Doug just funded 1,000 computer scientists for 7 years in ECP, so we got close to that scale. So we know that this is doable. It's a few $100 million a year, right? You need government commitments to field 2 or 3 of these big machines. Why 2 or 3? Because you've got several different technology paths, and we have no idea which one's going to emerge as the correct path, right? These are probably billion-dollar machines. I'll say more about cost in a minute. We've got to figure out how to scale these things up, all kinds of technical issues. We've got to figure out how to fab them. Are these superconducting transmon circuits? Are they photon-based? Are they ion trap or neutral atom-based? Are they quantum dots? Are they maple-leaf particle-based or whatever, right? I love Majorana particles. There's lots of building blocks engineering in doing this, right? How local, is this local, non-local, distributed, right? But here's an interesting thing. You're not going to have a leadership quantum computer without it being embedded in a leadership class classical computer. And I'll talk more about that in a second. We need a lot more algorithms. The reason for this, and this was also discussed yesterday, there's 2 general classes of quantum algorithms. Fast ones and not so fast ones. We need more algorithms like Shor's that have super polynomial or exponential speedups. And we need, there's lots of algorithms that are similar to Grover's that give you kind of quadratic speedup, but that's not enough. You can't you're not going to take any quantum money to the bank on Grover's, okay? So you've got to do this, but there's some other challenges. Many of these algorithms start their complexity analysis at the assumption that you've got a prepared state on the machine where you're loading in classical data and preparing the state. Right now, that consumes all of your entire coherence budget. So obviously we have to fix that, right? So anybody who's talking about applying quantum computers today to problems that have real amounts of classical data they have to ingest, they're pulling your leg because we can't do that, right? So not in AI, not in operations research if it has real data, not in biology, not in drug design, right? So the question is, what problems could we make progress on? And the reason for this, and I'll give these slides to everybody. So the top part here is just how to think about this problem. You spend a bunch of time loading classical data and doing state preparation, then you get to compute in quantum happy space, and then you spend a bunch of time trying to extract meaningful results from that state into some classical data. And then you do this over and over again, right? Because you're sampling. So the result of this often is people don't understand that you're not actually solving the problem often. Often you're just getting some hint that the problem is solvable, not that you actually have the result. So this is really a different way of thinking, and we need a lot more people to help think about this. I talked about large-scale quantum systems being embedded in large-scale classical systems. Why is that? Because the programming paradigm for these machines, or the computing paradigm, looks like this circle thing here. You're going to prepare some states, you're going to transform it, you're going to measure it, you're going to post-process measurement to figure out what went wrong or how you can improve it, adjust the program in loop. And you're going to do that hundreds or thousands of times. That's how you solve a quantum variational optimization problem. It's how you would even solve most quantum problems. And if you look at the toolkits, they even explicitly encode this. This is a beautiful toolkit here. So it's probably from the Xanadu box. But the pink part here is the classical computation, and the quantum part's in this, whatever color this is, gray here. And you can see this, the quantum piece is inside a giant multi-nested loop, okay? So the classical machine is invoking thousands of iterations of the quantum thing. Here's another one. Here's one general way of thinking about this. So you've got the quantum machine on the left, classical machine on the right. You're deriving the circuit, you're running stuff, throwing away state, swapping, measuring something, computing some cost, doing it again, right? Classical machine tightly coupled to the quantum machine. Penny Lane quantum toolkit, same thing. They've got lots of beautiful graphics in their user manual, but you've got these quantum components in the green here and the classical components in the yellow, same thing. These code loops are tied together. If you look at Google's quantum AI stack, same thing, right? We've got TensorFlow, Keras infrastructure for machine learning on the left, that's classical, and the quantum aspects of it on the right in blue, and these are tightly coupled. And when you build a network, you freely integrate the quantum and the non-quantum elements. And so we've got to be thinking about these as tightly coupled accelerators, and often as tightly coupled or more tightly coupled than current accelerators we have, because many of the quantum error correction schemes require classical measurements continuously on probe bits or probe qubits to adjust the composition of the circuit in real time. Think of this as modifying the program in real time to compensate for errors in the hardware. That's a much tighter coupling than we think about classical CPUs to GPU coupling, for example, right? So what are some real targets that we might use to drive this? I'm just going to talk about Hamiltonians here. All right, there was a great paper out of the ETH group last year, or 21, I guess 2 years ago, where they did a very detailed analysis on using quantum computers to solve catalysis problems. And I don't have time to go through it. I gave you the visual guide here, but basically, to do this problem, they need thousands of qubits and billions of trillions of gate applications, right? Similar analysis for lots of groups. Same analysis for the best presentation so far of somebody trying to do a Shor's factoring problem, 6 billion gate applications on 6,000 logical qubits, right? So what is that going to cost? This is a fun exercise I did the last couple of days. By the way, you want to follow along in this, there's a website here, how should quantum computation be priced? These guys went out and did a survey of all the currently available quantum systems this past summer and how much they're charging for them. And the average cost is 5 cents per qubit second, except for Rigetti, which was charging 1 cent per qubit second. But that's what's happened to Rigetti, by the way. Chad's really wonderful. I feel bad for him. This is their stock price, and they're getting delisted from the NASDAQ because they've gone bankrupt, basically. So people have worked out 3 hard examples in quantum, right? These are solving real chemistry problems, electronic structure of cytochrome P450, the cofactor cluster that's in nitrogenase molecule, which is worth probably $1 trillion a year in the fertilizer market. And then another in factoring, a Shor's algorithm. And here's the costs, right? The current pricing to solve that P54 problem, $5 billion to run that code. For the second problem, for working out the ground state electronic structure of nitrogenase, $20 billion at the current cost. Factoring a 2,000-bit RSA integer, $21.6 billion at the current cost, right? Now, how can we make any sense out of this? So let's say you were going to stand up. You're trying to make a pitch, right, to agency. You want to build a real quantum computer that's going to solve a real problem, right? You're going to need 1 million qubits to get 1,000-ish logical qubits. You want to run it for a year, okay? That's 23 million seconds. If you price it out today, right, that's $50,000 per second, right? That's pretty good money if you can make that, right? You multiply this out, a year at 1 million qubits, 30, I know, I gotta go, I'm almost done. This turns out to be $1.6 trillion a year, okay? So does this make any sense? Well, if we can get qubits to be reduced by a factor of 1,000 or maybe 10,000, 100,000, right? You can look whether we've done that in the past with transistors. So maybe makes no sense, right? So why zeta scale? I've only got a couple more slides. The reason that we need to work on this is because the rest of the world is going to be burning all their money on quantum, right? And something has to actually power real progress, and that's going to be progress on classical machines. So, you know, we can talk about this. People raised all kinds of issues the other day. Now, we're not the only ones thinking about this. There was a paper out of NUDT a couple years ago, and we've done this comparison of what they were throwing out as a target, and how does that compare to Frontier? Doug's seen this before. And I colored in green the rates of improvement that we've seen historically, right? That might be crazy. So in terms of power, well, maybe we can get there because it's only a CAGR of like 9%, right? And floor space, okay, that's easy, right? But some of these things will require year-on-year aggregate rates of improvement of 50%, which is much faster than Moore's law at the heyday, right? So this is unlikely to happen, and this was, I think, Satoshi had a slide very similar, right? But what are some reasonable planning targets? Well, for a machine maybe in 28, right? If you said 10 exaflops, FE64, through the magic of low precision, you could probably get somebody to make 100 exaflops in maybe BFP16 or FP8, right? We can almost train models in FP8 now. And by 2032, right, you can probably hit a zeta, not in 64-bit, but probably in some low precision. So the real question is, could we hit any of these, right? Are these things still on the trajectory where GPUs will go? Of course, we're going to answer the question, quantum doesn't matter. But maybe we need to be pushing much more aggressively in mixed precision, right? How little 64-bit can we get away with to actually solve real problems? That's the end of my talk. Thank you.